In 1965, Richard Feynman stood in front of a classroom at Cornell University and made a statement that would reveal something fundamental about how he approached physics. He said that if you think you understand quantum mechanics, you don't understand quantum mechanics. This wasn't pessimism, it was precision. And what made this statement remarkable wasn't its paradoxical sound, but that it came from a man who had just won the Nobel Prize for formulating the mathematical framework that allowed physicists to calculate quantum phenomena with extraordinary accuracy. Feynman had built the tools that let us predict the behavior of subatomic particles to within 1 part in a billion, yet he insisted that understanding and calculating were not the same thing. This distinction wasn't philosophical posturing. It reflected a documented pattern in how Feynman approached cosmological questions throughout his career, one that separated him from nearly every other physicist of his generation. If you enjoy this kind of evidence-based content, like the video, subscribe to the channel, and turn on notifications. There are many other videos on the channel built the same way, and if this topic interests you, you'll likely enjoy what's already there. The evidence for Feynman's different approach appears most clearly not in his famous lectures or popular books, but in the actual working papers and correspondence archived at Caltech. Between 1948 and 1985, Feynman produced thousands of pages of calculations, diagrams, and notes. What stands out when you examine these documents is what's missing. Where contemporaries like Steven Weinberg or Abdus Salam filled notebooks with grand unified theories and attempts to connect all forces of nature into single elegant frameworks, Feynman's papers focus almost exclusively on specific, solvable problems. He calculated the precise energy levels of hydrogen atoms. He worked out exact scattering cross-sections for electron-positron collisions. He derived the behavior of liquid helium at temperatures near absolute zero. Each calculation addressed a question that could be answered definitively, tested experimentally, and closed. This wasn't because Feynman lacked ambition or vision. The archive shows dozens of attempts at broader theories, but nearly all of them stop mid-calculation with notes like, "doesn't work," or "circular," or simply a question mark. He abandoned approaches that couldn't be tested or that relied on assumptions he couldn't verify. This pattern becomes cosmologically significant when you look at how Feynman approached the largest questions physics confronts. In 1963, the discovery of quasars presented the astronomical community with objects that appeared to be emitting as much energy as entire galaxies from regions smaller than our solar system. The mainstream response, documented in journals like the Astrophysical Journal and Nature, was to immediately propose mechanisms involving exotic physics, supermassive black holes, matter-antimatter annihilation, gravitational collapse scenarios that push general relativity to its limits. Feynman's response, preserved in his correspondence with astronomer Martin Schmidt at Caltech, was different. He asked what the actual measurements showed. Schmidt's team had observed spectral lines shifted toward the red end of the spectrum by specific, measured amounts. They had measured brightness variations on specific timescales. They had detected radio emissions with particular characteristics. Feynman's letters don't propose explanations. Instead, they ask whether each measurement had been checked against systematic errors, whether alternative interpretations of the spectral data had been ruled out, whether the brightness variations could be artifacts of the measurement technique. Only after establishing what was actually known did he consider what might explain it. And even then, his notes show him constantly distinguishing between what we can calculate and what we think might be true. This distinction mattered because cosmology, more than any other field of physics, deals with phenomena we cannot directly manipulate or repeat. We observe one universe. We cannot run controlled experiments on galaxy formation or stellar evolution. We cannot rewind cosmic history and test different initial conditions. This places cosmology in a fundamentally different epistemic position than laboratory physics, and Feynman never forgot this. In his 1964 lecture series on the character of physical law, he spent an entire lecture discussing the difference between astronomical observation and experimental verification. He pointed out that when we observe distant galaxies, we're seeing light that left those galaxies millions or billions of years ago. We're not watching those galaxies as they are now. We're watching a historical record, and we're watching it from exactly one vantage point. We cannot move to see the same event from a different angle. We cannot replay it under controlled conditions. Every conclusion we draw must account for these constraints, and Feynman insisted that cosmological theories be honest about what they could and couldn't actually demonstrate. The practical effect of this approach shows up most clearly in Feynman's response to the big questions of cosmology that dominated physics in the second half of the 20th century. Consider the question of whether the universe is infinite or finite? This was a major topic of debate among physicists and cosmologists throughout the 1960s and 70s. Theoretical models existed for both possibilities. General relativity allowed for both open, infinite universes and closed, finite ones. The question seemed fundamental to understanding the cosmos. Yet Feynman, in multiple recorded lectures and published papers, consistently refused to take a position on the matter. Not because he found both possibilities equally plausible, but because he couldn't see how either claim could be definitively tested with available observational techniques. We can only observe a finite portion of the universe, limited by the speed of light and the age of the universe. No amount of telescope time can tell us what exists beyond that observable horizon. Therefore, claims about the infinite or finite nature of the total universe remain, in Feynman's framing, neither true nor false but simply untestable. And untestable claims, no matter how elegant or intuitive, fell outside what he considered legitimate physics. This wasn't skepticism for its own sake. Feynman worked extensively on problems in quantum electrodynamics that involved infinite series and required careful mathematical treatment of infinities. He understood that infinity was a useful mathematical concept. What he rejected was treating the physical existence of infinity as an established fact when no observation could distinguish between a very large finite universe and a truly infinite one. The distinction might seem pedantic, but it reflects something deeper about how Feynman thought about the relationship between mathematics and physical reality. Mathematics can describe infinities perfectly well. We can manipulate infinite series, work with infinite sets, prove theorems about infinite dimensional spaces. But the question of whether anything infinite actually exists in the physical world is different. It's an empirical question, and empirical questions require empirical evidence. Without a measurement that could distinguish infinite from arbitrarily large, the question remained open, and Feynman treated it as such. This same principle guided his approach to cosmic origins. The 1960s and 70s saw intense theoretical work on the very early universe, particularly on what happened in the first fractions of a second after the Big Bang. Steven Weinberg's 1972 book, The First 3 Minutes, presented a detailed narrative of cosmic evolution starting from 10 to the power of negative 43 seconds after the initial singularity, the Planck time. The book became enormously influential, shaping how both physicists and the public thought about cosmic origins. Feynman read it. His personal copy, now in the Caltech archive, contains margin notes. These notes reveal a consistent pattern. Wherever Weinberg describes events that follow from well-tested physics, extrapolated into extreme conditions but still within the regime where quantum field theory and general relativity make definite predictions, Feynman's notes indicate agreement or ask specific technical questions. But wherever the narrative pushes beyond what could be calculated from established principles, the margin notes become skeptical. Next to discussions of the initial singularity, Feynman wrote, "How do we know?" Next to speculations about physics before the Planck time, he wrote, "No theory here." These weren't rejections of Weinberg's work. They were reminders to himself about where calculation ended and speculation began. The distinction mattered because it affected what questions Feynman thought physics could legitimately try to answer. Most cosmologists treated the question, "What happened before the Big Bang?" as a scientific question in principle, even if we didn't yet have the tools to answer it. The assumption was that eventually, with better theories and better observations, we would be able to say something definite about the earliest moments of cosmic history, perhaps even about what, if anything, preceded them. Feynman's position, expressed most clearly in his 1980s lectures at Caltech, was different. He argued that asking what happened before time itself existed was not a scientific question but a confusion of language. If time itself began at the Big Bang, then before has no meaning in that context. It's not that we don't know what happened before. It's that the question assumes a framework, the existence of time, that doesn't apply to the situation being asked about. This wasn't a claim about what did or didn't happen. It was a claim about what we could meaningfully ask given the structure of physics itself. This linguistic precision extended to how Feynman talked about physical law. Most physicists, when discussing fundamental laws, speak as if these laws govern or control the universe. We say that gravity makes planets orbit stars, that electromagnetism makes charges attract and repel, that the laws of thermodynamics require entropy to increase. This language suggests that physical laws are somehow prescriptive, that they impose requirements on how nature must behave. Feynman found this language misleading. In multiple lectures, He pointed out that physical laws don't make anything happen. They describe patterns we observe. When we say that F equals ma, we're not saying that force causes mass times acceleration. We're saying that in every situation we've tested, when we measure force, mass, and acceleration, we find that the numbers satisfy this relationship. The law is a summary of observations, not an explanation of why those observations hold. This might seem like a minor semantic point, but it changes how you approach cosmological questions. If laws describe rather than prescribe, then finding the right description becomes the goal, and questions about why those particular laws hold rather than others move outside the domain of physics into philosophy or metaphysics. The practical consequence of this view appears in Feynman's approach to cosmic fine-tuning arguments. Throughout the 1970s and 80s, physicists increasingly noted that the fundamental constants of nature, things like the strength of gravity, the mass of the electron, the speed of light, appeared to be precisely calibrated to allow for the existence of stars, planets, and ultimately life. Change any of these constants by even a small amount, and you get a universe where stars never form, or where matter never clumps into structures, or where chemistry cannot occur. This observation led many physicists to argue that the universe must be specially designed, or that we must be living in one of many universes with different constants, with ours being one of the rare ones suitable for life. Both proposals, design and multiverse, became major topics of cosmological discussion. Feynman's response to both, documented in lecture notes and correspondence, was to point out that neither proposal made any testable predictions. The design hypothesis didn't specify who designed it or why or how, and therefore couldn't be tested. The multiverse hypothesis required the existence of other universes we could never observe or interact with, and therefore also couldn't be tested. Both might be true. Neither could be established or ruled out using the methods of physics. Therefore, Feynman argued, either deserved the label of scientific theory, regardless of how many physicists found them appealing. This doesn't mean Feynman thought the fine-tuning observations were unimportant. He acknowledged that the precise values of physical constants posed a genuine puzzle. What he rejected was treating appeals to design or multiverse as solutions to that puzzle rather than as restatements of it in different language. Saying the universe is designed doesn't explain why the constants have the values they do. It just pushes the question back one level to asking why the designer chose those particular values. Similarly, saying our universe is one of many doesn't explain why the ensemble of universes has the property of generating constants suitable for life. Both proposals replace one mystery with another, equally unexplained mystery. Feynman preferred to leave the question open rather than to pretend it had been answered. This preference for acknowledged ignorance over false certainty shaped Feynman's entire relationship with cosmology. Where other physicists built elaborate models of cosmic inflation, dark matter, dark energy, and quantum gravity, Feynman focused on what could be calculated from established principles and what couldn't. His lecture notes from the early 1980s include extensive discussions of what we actually know about the large-scale structure of the universe. We know galaxies exist and that they cluster into groups and superclusters. We know the universe is expanding, with distant galaxies receding from us at speeds proportional to their distance. We know the cosmic microwave background exists, and has a nearly uniform temperature of about 2.7 Kelvin with tiny fluctuations at the level of 1 part in 100,000. We know the light elements hydrogen, helium, lithium exist in specific ratios that match predictions from Big Bang nucleosynthesis. Each of these facts comes from direct observation and can be verified independently by different methods. Each one constrains possible histories of the universe. But Feynman emphasized that knowing these facts doesn't automatically tell us what happened during epochs we cannot directly observe or what mechanisms drove the processes that produced the structures we see. Consider cosmic inflation, the theory that the early universe underwent a period of exponential expansion driven by a special energy field. Inflation was proposed in 1981 by Alan Guth to solve several problems with the standard Big Bang model, particularly the horizon problem and the flatness problem. The horizon problem asks why regions of the universe that were never in causal contact with each other have the same temperature. The flatness problem asks why the density of the universe is so close to the critical value that determines whether the universe is open or closed. Inflation solves both problems elegantly by proposing that all regions of the observable universe were once in causal contact before inflation separated them, and that inflation drove the universe toward flatness regardless of its initial state. The theory made specific predictions about the pattern of fluctuations in the cosmic microwave background, predictions that were subsequently confirmed by observations from satellites like COBE and WMAP. Many cosmologists treat inflation as essentially established fact. Feynman's notes on inflation, written in the early 1980s after several discussions with Goose and other inflation theorists, show a more cautious assessment. He acknowledged that inflation solved the problems it was designed to solve and that its predictions matched observations. But he pointed out that the theory required introducing a new field, the inflation field, with very specific properties. This field had to start in a particular high-energy state, then decay in a particular way, all while producing exactly the right amount of expansion to solve the horizon and flatness problems without creating new problems. The field had never been detected independently. Its properties were chosen specifically to make inflation work. In Feynman's framing, this meant that inflation was less an explanation of cosmic structure and more a description of what kind of mechanism would be needed to produce the structure we observe. It answered the question, what sort of process could generate the observed universe, but not the question, did this process actually occur? The distinction matters because we can imagine many possible mechanisms that would produce similar results. Without independent evidence for the inflation field, we cannot distinguish between inflation and other possible mechanisms, some of which might not have been invented yet. This skepticism wasn't unique to inflation. Feynman applied the same standard to dark matter and dark energy, the two components that make up approximately 95% of the total mass energy content of the universe according to current cosmological models. The evidence for dark matter comes primarily from observations of how galaxies rotate and how galaxy clusters move. Visible matter alone cannot account for the observed velocities. Either there is additional matter we cannot see, or our understanding of gravity on galactic scales is wrong. Most cosmologists favor the additional matter hypothesis, called dark matter, because it fits more naturally into existing theoretical frameworks. The evidence for dark energy comes from observations of distant supernovae, which show that the expansion of the universe is accelerating. This acceleration requires some form of energy with unusual properties, either a cosmological constant or a dynamic field that changes over time. Again, most cosmologists favor the energy hypothesis because it fits more naturally into general relativity. Feynman died in 1988, before the 1998 discovery of cosmic acceleration that led to the dark energy hypothesis, but his notes include discussions of dark matter from the 1970s and 80s. His position was characteristically careful. He agreed that the observations required explanation. Either there was additional matter, or gravity worked differently on large scales, or the observations themselves were being misinterpreted in some subtle way. All three possibilities remained open. The dark matter hypothesis was the simplest in the sense that it required the least modification to existing theory. But simplicity alone didn't make it true. What was needed was direct detection of dark matter particles or some observation that could only be explained by dark matter and not by modified gravity or observational error. Until such evidence appeared, Feynman treated dark matter as a promising hypothesis but not an established fact. This might seem like excessive caution, but it reflects an important principle. In science, we often have multiple explanations for the same observations. Choosing between them requires not just theoretical elegance but differential predictions, tests that give different results depending on which explanation is correct. Without such tests, we risk mistaking our preferred explanation for the only possible one. The same principle applies to questions about the ultimate fate of the universe. Will the universe continue expanding forever, eventually growing cold and dark as stars burn out and black holes evaporate? Or will expansion eventually reverse, leading to a big crunch where all matter collapses back to a singularity? Or will something else entirely happen? These questions depend on the total energy density of the universe and on the nature of dark energy. Current observations suggest continued expansion and eventual heat death, but the measurements have uncertainties, and the dark energy models making these predictions remain poorly understood. Feynman's approach to such questions, documented in his final lectures at Caltech, was to distinguish clearly between what observations told us about the current state of the universe and what theoretical models predicted about its future. We can measure the current expansion rate, the current matter density, the current temperature of the cosmic microwave background. These are facts we can establish with telescopes and instruments. What will happen trillions of years from now depends on models that extrapolate current physics far beyond the regimes where we've tested it. The extrapolation might be correct. It might not. We won't know until we develop better observations or better theory. And even then, we'll be making predictions about epochs so distant that verification is impossible. This acknowledgement of limits was central to how Feynman thought about humanity's place in the cosmos. Many physicists and cosmologists speak of understanding the universe, of uncovering the fundamental laws that govern all of reality, of approaching a theory of everything that would explain all physical phenomena from a single set of principles. Feynman was skeptical of this language, not because he doubted that physics could make progress or that deeper principles might exist, but because he thought the phrase, understanding the universe, assumed too much. We understand the specific phenomena we've studied and tested. We understand how atoms work, how light propagates, how planets orbit, how stars burn. Each of these domains has been investigated in detail, and we have mathematical frameworks that let us make precise predictions about them. But the universe is large and old and complex. Most of it remains unobserved. Most of cosmic history occurred before humans existed to observe it. The confidence that our current theories capture something fundamental about all of reality, everywhere and always, struck Feynman as premature. This wasn't a claim that physics couldn't progress or that we should stop trying to find deeper explanations. Feynman spent his entire career working on exactly such explanations. It was a claim about epistemic humility, about recognizing the difference between what we've actually tested and what we assume must be true. Every physical theory has a domain of validity, a range of conditions under which it's been tested and found accurate. Newtonian mechanics works extraordinarily well for objects moving much slower than light in gravitational fields much weaker than those near black holes. General relativity extends this domain to higher speeds and stronger fields. Quantum mechanics works for microscopic systems where quantum effects dominate. Quantum field theory combines quantum mechanics and special relativity for particle physics. Each theory has been tested extensively within its domain. None has been tested everywhere. When we use these theories to make claims about the entire universe or about epochs like the first instance after the Big Bang, we're extrapolating far beyond what we've directly verified. The extrapolation might be legitimate. Often it is, but Feynman insisted on marking clearly where direct evidence ended and extrapolation began. This marking became particularly important when discussing the question of whether physical laws are the same everywhere in the universe. Most cosmological models assume that the laws of physics we measure in laboratories on Earth apply throughout the cosmos, at all times and in all places. This assumption, called the cosmological principle, is essential to making cosmology tractable as a science. If physical laws changed from place to place or from time to time in arbitrary ways, we couldn't make predictions about distant regions or early epochs. But the cosmological principle is an assumption, not an established fact. We can test it in nearby regions in recent times by observing how stars and galaxies behave and checking whether their behavior matches what our theories predict. So far, observations confirm that the same physics applies, at least throughout the observable universe and back to times we can probe with telescopes. But we cannot test whether the laws remain the same in regions beyond our observational horizon or during epochs before the universe became transparent to light. Feynman's point was that acknowledging this limitation doesn't make cosmology impossible, but it does require honesty about what we know directly and what we assume for theoretical convenience. This honesty extended to how Feynman talked about scientific consensus. In most fields of physics, strong consensus emerges relatively quickly when theories are tested and confirmed. The scientific community agreed on quantum electrodynamics within a decade of its formulation because the theory made precise predictions that were verified by multiple independent experiments. General relativity gained widespread acceptance after the 1919 solar eclipse observations confirmed its prediction of light bending, and subsequent tests continued to confirm its predictions. These consensuses emerged from accumulated experimental evidence, not from theoretical elegance or majority voting. Cosmology, however, operates differently. Many cosmological theories cannot be tested directly because they make predictions about unobservable regions or untestable epochs. Consensus in cosmology often forms around theories that are mathematically elegant, that solve outstanding puzzles, that fit with other established physics, but that lack the kind of direct experimental confirmation that would be required in other fields. Feynman didn't reject cosmological theories for this reason, but he did insist on treating them differently from experimentally verified physics. A cosmological model might be the best available explanation for observations. It might be supported by strong indirect evidence, but without direct tests, it remained a model, a framework for organizing observations, not an established description of reality. This distinction shows up most clearly in Feynman's lectures on the nature of scientific knowledge. In a famous lecture from 1964, he discussed how scientific knowledge differs from other forms of knowledge. He described science as a process of constantly testing our ideas against nature, and keeping only those ideas that survive testing. But he emphasized that this process only works when nature can actually answer our questions, when we can perform experiments, or make observations that distinguish between competing explanations. In areas where such tests aren't possible, science loses its defining characteristic. We might still reason carefully, develop consistent mathematical models, make logical arguments, but we're doing something closer to mathematics or philosophy than to experimental science. Cosmology, Feynman suggested, sits on the boundary between these domains. When it makes predictions about observable phenomena, it's science. When it speculates about unobservable regions or untestable scenarios, it becomes something else, still valuable perhaps, still interesting, but no longer constrained by the same empirical discipline. This boundary consciousness influenced how Feynman approached questions about life in the universe. The question of whether life exists elsewhere has intrigued humans for centuries, and by the 1960s and 70s, it had become a legitimate topic of scientific investigation. The Drake equation, formulated in 1961, attempted to estimate the number of communicative civilizations in our galaxy by multiplying together various factors: the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction that actually develop life, the fraction where life becomes intelligent, the fraction that develop communication technology, and the length of time such civilizations remain detectable. The equation became widely used in discussions of extraterrestrial life. Feynman's response to it, recorded in lecture notes from the 1970s, was to point out that we only have reliable values for the first two factors. We can estimate how often stars form and what fraction have planets. For all the other factors, we have exactly one data point: Earth. We don't know how common life is on potentially habitable planets because we've only found life on one planet. We don't know how often life becomes intelligent or develops technology because we've only observed one instance of each. Multiplying together wild guesses doesn't produce a meaningful estimate. It produces a number whose uncertainties are so large as to make it useless. This didn't mean Feynman thought searching for extraterrestrial life was pointless. He supported such searches and considered them scientifically valuable because they were attempts to answer the question through observation rather than speculation. But he rejected the Drake equation as providing any real insight into how common life might be. The equation's popularity, he suggested, came not from its scientific value but from its ability to organize our ignorance into a structured form. It identified the questions we would need to answer to estimate the prevalence of life, but it didn't actually answer those questions. And without those answers, any estimate remained essentially arbitrary. You could plug in optimistic values and conclude the galaxy teems with civilizations. You could plug in pessimistic values and conclude we're alone. Both conclusions followed from the same equation. This made the equation a useful framework for discussion but not a tool for reaching definite conclusions. The same skepticism of premature quantification appears in Feynman's discussions of the origin of life on Earth. By the 1970s, researchers had conducted numerous experiments showing that simple organic molecules could form under conditions thought to resemble the early Earth. The Miller-Urey experiment of 1953 had produced amino acids by sparking electrical discharges through a mixture of water, methane, ammonia, and hydrogen. Subsequent experiments produced other organic compounds, including nucleotide bases, the building blocks of DNA and RNA. These results suggested that the chemical precursors of life could arise naturally from simple starting materials. Many researchers treated this as strong evidence that life's origin was a natural, perhaps inevitable, consequence of chemistry on any planet with the right conditions. Feynman's assessment, recorded in discussions with biochemists at Caltech, was more reserved. He agreed that the experiments showed organic molecules could form naturally, but the gap between producing amino acids in a test tube and producing a living cell remained enormous. A living cell is not just a collection of organic molecules. It's a system with extraordinary organization, with DNA encoding information, RNA translating that information, proteins carrying out functions, all enclosed in a membrane that maintains a chemical environment different from the surroundings. No experiment had come close to producing such organization from simple starting materials. The Miller-Urey experiment, and its successors showed that the first step, producing organic building blocks, was relatively easy. They said nothing about how the remaining steps occurred. Feynman didn't claim those steps were impossible or required special intervention. He claimed we didn't yet understand them well enough to make confident statements about how likely or inevitable they were. This pattern of distinguishing what we've demonstrated from what we assume carried through to Feynman's discussions of consciousness and intelligence. Some physicists and cosmologists have argued that the universe must be comprehensible to human minds, that the fact we can understand physics at all tells us something deep about the relationship between mind and cosmos. The argument suggests that if the universe were truly random or arbitrary, we couldn't find patterns in it, couldn't formulate laws, couldn't predict future events. The fact that we can do these things implies some kind of match between the structure of our minds and the structure of reality. Feynman found this argument backwards. We've evolved in this universe, shaped by the same physical laws we're trying to understand. Our mental capacities developed because they helped our ancestors survive in a world governed by those laws. Of course we find patterns, because our brains evolved to find the patterns that matter for survival. But this doesn't mean the universe was designed to be comprehensible. It means our comprehension was shaped by the universe. The match between mind and reality exists because minds that didn't match reality didn't survive to reproduce. This evolutionary explanation, Feynman argued, removed any need to invoke special cosmic design or deep metaphysical connections. It was sufficient to explain the observed facts without adding additional assumptions. Similarly, when discussing the apparent improbability of our existence, Feynman pointed out that we should expect to find ourselves in conditions compatible with our existence. This sounds trivial, but it carries significant implications. If the only conditions under which observers can exist are the rare ones where fundamental constants allow for stars, planets, chemistry, and biology, then observers will necessarily find themselves in those rare conditions. This doesn't mean those conditions are common, or that the universe was designed to produce them. It just means that in a large enough universe, even very rare conditions will occur somewhere, and observers will necessarily find themselves in one of those somewheres. This principle, sometimes called the anthropic principle, has been used to argue both for and against various cosmological models. Feynman's take was that the principle itself was just a tautology, a recognition that our observations are conditioned by our existence. It didn't explain why the constants have their particular values or why the universe contains the structures it does. It just reminded us not to be surprised that we find ourselves in conditions compatible with our existence. These discussions of fine-tuning, consciousness, and the anthropic principle reveal a consistent theme in Feynman's cosmological thinking. He resisted explanations that invoke special purposes or cosmic designs, not because he had philosophical objections to such ideas, but because they didn't add explanatory power. Saying the universe was designed to support life doesn't tell you anything about how stars form, or why the electron has its particular mass, or how DNA replicates. It's an additional claim layered on top of the physics, one that doesn't help you calculate anything or predict any observations. Feynman preferred explanations that stayed close to what could be calculated and tested. If you could derive a prediction from established physics and verify it through observation, you had learned something. If you could only tell a story about why things might be the way they are without being able to test that story, you hadn't really explained anything, no matter how satisfying the story felt. This preference for calculation over narrative shaped Feynman's entire pedagogical approach. When he taught physics, documented in his famous lectures on physics from the early 1960s, he focused relentlessly on working through specific examples and showing students how to calculate actual results. He would introduce a concept, immediately apply it to a concrete problem, solve that problem in detail, then move to another problem that added one new element. This built understanding through accumulated experience with calculations, not through abstract principles stated at the beginning. The same approach appears in his cosmological discussions. Rather than starting with grand statements about the nature of the universe, he would start with specific observations. What does the spectrum of distant galaxies tell us? How fast are they moving? What does that tell us about the expansion rate? Each question built on the previous one, and each answer came from working through the mathematics connecting observations to conclusions. This emphasis on working through details rather than accepting broad claims had profound implications for how Feynman thought about scientific education and public understanding of cosmology. He was deeply concerned that popular presentations of cosmology often gave the impression that we understood far more than we actually did. Books and television programs spoke confidently about the first moments after the Big Bang, about parallel universes, about the fate of the cosmos trillions of years hence, without always making clear that these were theoretical extrapolations, not established facts. Feynman worried that such presentations did the public a disservice by creating false confidence and by obscuring the actual process of science, which involves uncertainty, revision, and constant testing against nature. In his own popular lectures, he made a point of distinguishing clearly between what physics could definitely say and what remained uncertain or speculative. He would explain a concept, then explicitly state what observations supported it and what questions remained open. This made his lectures less dramatic than those of some contemporaries, but it also made them more honest about the actual state of knowledge. The clearest example of this honesty appears in Feynman's discussions of quantum mechanics and its implications for cosmology. Quantum mechanics describes the behavior of microscopic systems with extraordinary precision. It predicts the energy levels of atoms, the rates of radioactive decay, the interference patterns of electrons, all confirmed by countless experiments. But applying quantum mechanics to the universe as a whole raises conceptual difficulties. In standard quantum mechanics, a system exists in a superposition of all possible states until measured, at which point it collapses to a definite state. But if the universe itself is a quantum system, what measures it? What causes it to collapse to one definite state rather than remaining in superposition? Various interpretations of quantum mechanics give different answers, but none has been definitively confirmed or ruled out. Some interpretations, like the many worlds interpretation, suggest that the universe doesn't collapse at all but branches into multiple versions, each representing different possible outcomes. This has been used to support multiverse cosmology. Feynman's view, expressed in multiple lectures and papers, was that all interpretations of quantum mechanics that made the same predictions were equally valid for purposes of calculation, but that choosing between them required empirical evidence we didn't yet have. The many worlds interpretation wasn't wrong, but it also wasn't established as true. It was one possible way of thinking about quantum mechanics that happened to appeal to some physicists, but that didn't make different predictions from other interpretations. Without different predictions, there was no way to test which interpretation actually described reality. This refusal to choose between empirically equivalent theories extended beyond quantum mechanics. Throughout physics, we often have multiple mathematical frameworks that describe the same phenomena. Classical mechanics can be formulated using Newton's laws, or Lagrangian mechanics, or Hamiltonian mechanics. All three give identical predictions for observable quantities but think about the underlying physics differently. Feynman himself developed an entirely new formulation of quantum mechanics based on path integrals, different from the standard wave function approach but giving the same results. The question of which formulation was really true struck Feynman as misguided. They were all equally true in the sense that they all correctly described observations. They were all equally false in the sense that they were all mathematical models, abstractions from reality rather than reality itself. The choice between them came down to which was most convenient for the problem at hand, not which correctly represented some underlying metaphysical reality. This pragmatism about theoretical frameworks carried over into Feynman's view of what physics was ultimately trying to achieve. Many physicists speak of discovering the true laws of nature, of uncovering the real structure underlying physical phenomena. Feynman's goal was more modest. He wanted to find mathematical patterns that accurately described observations and made correct predictions. Whether those patterns represented some deeper truth about reality or were just convenient summaries of regularities, he considered an open question, one that physics couldn't definitively answer. This didn't mean he thought reality didn't exist independently of our observations. He clearly believed in an external world with definite properties. But he thought our access to that world came only through measurements, and that the structure we found in those measurements might tell us more about how we measure than about what we measure. The question of whether our theories carved nature at its joints or imposed artificial structure on something more complex or more simple remained, in his view, undecidable within physics itself. These philosophical positions had practical consequences for Feynman's research choices. While many of his contemporaries worked on grand unified theories of everything, and attempts to quantize gravity, Feynman focused on problems where calculation was possible and testing feasible. He worked on pattern models of nucleon structure, which helped explain how protons and neutrons behave in high-energy collisions. He developed theories of superfluidity that explained the strange behavior of liquid helium at low temperatures. He contributed to quantum computing by showing that quantum systems could in principle simulate other quantum systems more efficiently than classical computers could. Each of these projects addressed a specific phenomenon, made definite predictions, and could be tested against experiment. None of them promised to answer ultimate questions about the cosmos, or to unify all of physics into a single framework. But they advanced understanding in concrete, verifiable ways. This preference for concrete progress over grand synthesis was not universal among physicists. Many of Feynman's colleagues believed that physics was approaching a final theory, that the major pieces of the puzzle were in place, and that what remained was to fit them together into one unified picture. String theory, developed in the 1970s and 80s, represented the leading candidate for such unification. It proposed that all particles were actually tiny vibrating strings and that all forces emerged from different vibration modes of these strings. The theory was mathematically elegant and offered the hope of unifying quantum mechanics and gravity. Many brilliant physicists devoted their careers to developing it. Feynman was skeptical. Not because he thought the theory was wrong, but because it made no testable predictions. The energy scales at which string effects would become observable were so high that no conceivable experiment could reach them. The theory could be mathematically consistent and physically true, but without experimental tests, there was no way to know. Feynman's own work had been guided by constant interaction between theory and experiment. A theoretical idea suggested new experiments. Experimental results required theoretical explanation. This back and forth drove progress. String theory, as it was developed in the 1980s, lacked this experimental feedback. It was mathematics guided by aesthetic and logical considerations, not by nature's responses to our questions. Feynman did not claim string theory was wrong or that physicists shouldn't work on it. He claimed it wasn't yet physics in the sense that it couldn't yet be tested. It might become physics if someone found a way to derive testable predictions from it, or if experimental techniques advanced to the point where string effects became observable. But until then, it remained a mathematical exploration, valuable perhaps for training physicists and developing new mathematical tools, but not connected to the empirical world in the way established physics was. This assessment proved prescient. In the decades since Feynman's death, string theory has developed into an enormous mathematical edifice, has attracted many of the most talented theoretical physicists, has produced important results in pure mathematics, but still has not made a single testable prediction about the physical world. The debate over whether this matters, over whether theoretical elegance and mathematical consistency are sufficient without experimental confirmation, continues today. Feynman's position was clear. Without experimental tests, you can't know if you're describing nature or just exploring a beautiful but irrelevant mathematical structure. This insistence on empirical grounding also shaped Feynman's view of mathematical beauty in physics. Many physicists talk about theories being beautiful or elegant, and use these aesthetic criteria to judge between competing proposals. The most beautiful theory, they suggest, is more likely to be true. Nature, in this view, prefers mathematical elegance. Feynman granted that successful theories often turned out to be mathematically beautiful, but he rejected the idea that beauty was a reliable guide to truth. The history of physics included many beautiful theories that turned out to be wrong and many correct theories that initially seemed ugly or contrived. Maxwell's equations, now considered paradigms of mathematical elegance, were first formulated in a much more complex form with many arbitrary-seeming constants. Feynman's own path-integral formulation of quantum mechanics struck many physicists as bizarre when first proposed. Beauty emerged in retrospect, after a theory had been tested and found correct and physicists had time to reformulate it in its most compact form. But betting on beauty before testing was wishful thinking, not science. The same skepticism applied to arguments from simplicity. Physics often prefers simpler explanations over more complex ones, a principle called Occam's razor. Given two theories that both explain the observations, choose the simpler one. This principle has proven useful in practice, but Feynman pointed out that it was a heuristic, not a law of nature. Nature had no obligation to be simple. If experimental evidence required a complex theory, then that's what we needed, regardless of our aesthetic preferences. The job of physics was to describe nature accurately, not to satisfy our desire for simplicity. Sometimes nature turned out to be simple, which was convenient. Sometimes it didn't, which was inconvenient but still had to be accepted. These epistemological positions, developed over decades of research and teaching, formed the core of Feynman's distinctive approach to cosmology. Where others sought grand narratives and unified theories, he focused on what could be calculated and tested. Where others spoke confidently about the ultimate nature of reality, he distinguished carefully between observation and interpretation. Where others used cosmology to address questions of meaning and purpose, he insisted on staying within the domain where physics could actually provide answers. This approach didn't make him anti-cosmology. He engaged seriously with cosmological questions throughout his career. But it made him a particular kind of cosmologist, one who treated cosmology as an extension of physics rather than as a separate discipline with its own standards of evidence. The practical effect of this approach shows most clearly in what Feynman chose not to say. Most popular accounts of cosmology include grand statements about the universe's origin, its evolution, its ultimate fate. They tell stories about the Big Bang, about cosmic inflation, about dark energy driving accelerating expansion toward eventual heat death. These stories are based on our best current theories and observations, but they go well beyond what we can definitely establish. Feynman's accounts, by contrast, stick close to what observations actually show. The universe is expanding now. We can measure the expansion rate. Light from distant galaxies is redshifted by specific amounts. The cosmic microwave background has a specific temperature and pattern of fluctuations. These are facts. The narratives connecting these facts into a comprehensive story of cosmic evolution involve extrapolations and assumptions. Some of those extrapolations are very well justified. The match between predicted and observed abundances of light elements from Big Bang nucleosynthesis gives strong support to the hot, dense, early universe picture. But other parts of the story, particularly what happened in the first fractions of a second or what will happen trillions of years from now, involve much more speculation. Feynman kept the two categories distinct. This distinction becomes particularly important when thinking about what cosmology can tell us about questions beyond physics. Many people turn to cosmology hoping to find answers to questions like why the universe exists, whether it has a purpose, what our place in it is. These are deep questions that humans have asked for millennia. But Feynman argued that physics cannot answer them. Physics describes how things behave, what patterns they follow, what relationships hold between different measurable quantities. It doesn't and can't explain why those particular patterns hold rather than others. It doesn't and can't assign purpose or meaning to physical processes. These aren't failures of current physics. They're fundamental limitations of what physics as a discipline tries to do. Physics investigates the natural world by making observations and finding patterns in those observations. Questions about ultimate purpose or cosmic meaning don't fit into this framework because they're not questions about observable patterns. You can't measure meaning. You can't test purpose. Therefore, physics has nothing to say about them. Some people find this limitation troubling, as if it makes physics incomplete or inadequate. Feynman's view was different. He saw physics as one way of understanding the world, extraordinarily powerful within its domain, but not the only valid way of thinking about existence. Poetry, art, music, philosophy, religion, all provided different perspectives, asked different questions, sought different kinds of understanding. Physics didn't compete with these domains. It complemented them. Trying to make physics answer questions it wasn't designed to address did violence both to physics and to the questions. Better to recognize what physics could and couldn't do and to appreciate its achievements within its proper scope while seeking answers to other questions through other means. This integrated view of knowledge appears throughout Feynman's lectures and writings. He spoke eloquently about the beauty of nature revealed by physics, the wonder of understanding even a small piece of how the cosmos works. But he also recognized that scientific understanding didn't exhaust what could be known or experienced. When he looked at a flower, he saw the physics of photosynthesis, the evolution that shaped its structure, the chemistry of its pigments. But he also saw beauty, felt aesthetic pleasure, appreciated the flower as more than just a collection of molecules following physical law. These different ways of seeing didn't conflict. They enriched each other. The scientific understanding added depth to the aesthetic experience. The aesthetic response provided motivation for the scientific investigation. Neither was more real or true than the other. They were different aspects of a richer whole. This philosophical sophistication contrasts sharply with the simplistic scientism sometimes attributed to physicists, the view that science is the only valid form of knowledge and that everything can ultimately be reduced to physics. Feynman never made such claims. He argued forcefully for the value and importance of physics, defended scientific methods against pseudoscience and wishful thinking, insisted on empirical evidence and logical rigor within physics itself. But he also recognized that physics was a limited enterprise, powerful within its bounds but not universal. The question of whether life exists elsewhere in the universe was a scientific question that could eventually be answered through observation. The question of whether such life would be meaningful or valuable was not a scientific question. Physics could tell you how stars formed and evolved. It couldn't tell you whether to find that process beautiful or insignificant. Both types of questions mattered. Neither was answerable by physics alone. This recognition of limits extended to Feynman's view of his own understanding. Despite his Nobel Prize, his profound contributions to quantum field theory, his legendary ability to solve difficult problems, he consistently maintained that he didn't really understand quantum mechanics, didn't really understand why nature followed the patterns it did, couldn't really explain most of the fundamental questions about physical law. This wasn't false modesty. It was epistemological precision. He could calculate quantum mechanical processes with extraordinary accuracy. He could derive predictions from quantum field theory and verify them against experiment. But calculation isn't the same as understanding in the deep intuitive sense. We understand classical mechanics intuitively because we interact with classical objects every day. We develop mental models of how things move, how forces work, how systems behave. These models come from accumulated experience and let us predict behavior without formal calculation. Quantum mechanics doesn't work this way. Our everyday experience gives us no intuition for quantum behavior. We can learn the mathematics, master the formalism, calculate correct results. But the deep intuitive understanding, the feeling that we really grasp what's happening, remains elusive. Feynman was honest about this gap between calculation and comprehension. This honesty about the limits of understanding characterized Feynman's entire approach to physics and cosmology. He built a career on knowing what he knew and, more importantly, on knowing what he didn't know. He distinguished relentlessly between established fact and working hypothesis, between tested theory and speculative model, between what could be calculated from first principles and what required empirical input. These distinctions might seem pedantic or overly cautious to those seeking grand cosmic narratives. But they represented something deeper, a commitment to intellectual integrity that refused to claim more certainty than evidence warranted. This commitment to epistemic humility stands as perhaps Feynman's most important legacy for how we think about cosmology. The universe is vast, old, complex, and largely unobservable. We've managed to learn an enormous amount about it through clever observations and theoretical work. But what we know remains a small fraction of what could potentially be known, and what could potentially be known remains bounded by fundamental limits on observation and experiment. Acknowledging these limits doesn't diminish the achievement of cosmology. It defines what achievement in cosmology actually means. We've measured the expansion rate of the universe to a few % precision. We've mapped the distribution of galaxies across billions of light years. We've detected gravitational waves from black hole mergers billions of years in the past. Each of these accomplishments represents a triumph of human ingenuity and persistence. Each one pushes back the boundary of what we can definitely say about the cosmos. But the boundary remains. Beyond it lies not just the unknown but the possibly unknowable, questions that no observation can answer and no experiment can resolve. Feynman understood this better than most of his contemporaries. He worked at the boundary, extending it where possible but always marking clearly where solid ground ended and speculation began. This made his cosmology less dramatic than that of physicists who spoke confidently about parallel universes, the moment of creation, or the ultimate fate of reality. But it made his cosmology more honest, more grounded in what physics could actually demonstrate. And in the long run, this honesty served the field better than premature confidence. Many of the grand theories proposed in the 1970s and 80s have fallen by the wayside as new observations contradicted their predictions or as physicists realized they couldn't be tested. The careful, evidence-based approach Feynman exemplified has proven more durable. The consistency of Feynman's approach becomes even clearer when examining how he handled one of the most fundamental questions in cosmology: the nature of time itself. Most physicists treat time as a dimension similar to space, a background against which events occur. Einstein's relativity merged time and space into a single four-dimensional spacetime, and this framework has proven extraordinarily successful at describing everything from GPS satellites to black holes. But Feynman noticed something peculiar about how we actually use time in physics. In every equation, time appears as a parameter we measure with clocks, not as something we directly observe like we observe space by looking around us. We never see time. We see change, motion, evolution of systems. We infer time from these changes by assuming they occur at regular rates. But this assumption, while practical and well-tested in many contexts, becomes problematic when applied to the universe as a whole. The problem emerges most starkly when considering the early universe. Cosmological models describe time as beginning at the Big Bang, emerging along with space and matter and energy. But Feynman's notes from the late 1970s include a simple but devastating question: what does it mean to say time began if there was no time before to have a beginning? The statement sounds profound, but Feynman suspected it might be meaningless, a confusion of language rather than a description of physics. We use temporal words like began, and before, and after, but these words assume time already exists as a framework. Applying them to time itself creates circular logic. It's like asking what's north of the North Pole. The question seems to make grammatical sense, but it assumes a framework, directions on a sphere, that breaks down at the North Pole itself. Similarly, questions about what happened before the Big Bang assume a temporal framework that the Big Bang model says didn't exist yet. Feynman didn't claim this made cosmology impossible. He claimed it required extreme care in how we used language and what we claimed to know. When physicists described the universe at 1 second after the Big Bang or at 1 microsecond after or at the Planck time, they were calculating what physics predicted if you extrapolated current theories backward in time. These calculations might be correct, but the question of whether time itself had meaning at those early stages remained open. Our theories of physics all assume time as a given, a background against which processes occur. What happens when time itself is emerging as part of the process being described? We don't know. We don't have a theory of how time comes into being because all our theories assume it already exists. This is not a small technical detail. It's a fundamental gap in our understanding. This gap connects to broader questions about the relationship between physics and mathematics. Mathematics can manipulate time as a variable, can run equations backward to earlier and earlier moments, can approach t equals 0 asymptotically. But the mathematical manipulations don't automatically correspond to physical reality. Just because you can write down an equation describing conditions at t equals 10 to the power of negative 43 seconds doesn't mean those conditions actually existed in any meaningful sense. The correspondence between mathematics and physics requires verification through observation or experiment. For most of the history we're trying to describe with Big Bang cosmology, such verification is impossible. We cannot observe the universe at 1 microsecond after the Big Bang. We cannot run experiments that recreate those conditions. We're extrapolating from current physics into regimes far beyond what we've tested, and Feynman insisted on acknowledging the uncertainty inherent in such extrapolations. This acknowledgement extended to the concept of the universe itself. When cosmologists speak of the universe, they usually mean everything that exists, all of space and time and matter and energy. But Feynman pointed out that we only observe a tiny fraction of what might exist. Light from very distant regions hasn't had time to reach us yet. Light from very early times was scattered and absorbed before the universe became transparent. We see a limited slice of space-time, bounded by our position and by the age of the universe and by the speed of light. Everything beyond this observable region remains, by definition, unobservable to us. When we make statements about the universe as a whole, we're assuming that what we observe in our local region applies everywhere. This assumption might be correct, but it's an assumption nonetheless, one that cannot be directly verified because verification requires observation, and we cannot observe the unobservable regions. The implications of this limitation become particularly acute when considering theories about the multiverse. Several modern cosmological theories propose that our universe is just one of many, perhaps infinitely many, universes. The different universes might have different physical laws or different values of fundamental constants. Our universe has the particular properties it does not because those properties are special but because we happen to be in one of the universes where those properties allow observers to exist. This multiverse hypothesis has been invoked to explain the apparent fine-tuning of physical constants without requiring design or purpose. If there are infinitely many universes with different constants, some will inevitably have constants compatible with life, and observers will find themselves in those universes by selection effect. The logic is appealing, but Feynman's response to such proposals, recorded in discussions from the 1980s, focused on a crucial question: how do you test it? If other universes exist but cannot interact with ours in any way, cannot be observed or detected or communicated with, then their existence makes no testable predictions. The theory explains our observations, but so does the simpler theory that our universe is all that exists and happens to have these particular properties for reasons we don't yet understand. Both theories are consistent with everything we observe. Both could be true. But without some way to distinguish between them observationally, physics cannot prefer one over the other. The multiverse might exist. It might not. We have no way to know, and therefore, Feynman argued, we shouldn't treat it as established physics. It's a speculative idea that might someday lead to testable predictions, at which point it would become a legitimate scientific hypothesis. But until then, it remains in the category of interesting possibilities rather than confirmed facts. This standard had practical consequences for how Feynman thought physics should be taught and communicated. He was famous for his undergraduate lectures at Caltech, delivered in the early 1960s and later published as the Feynman Lectures on Physics. These lectures covered all of physics from mechanics through quantum mechanics and statistical physics. What's striking about them, especially the sections dealing with cosmology and astrophysics, is their emphasis on observational evidence and calculational detail. When Feynman discussed the expansion of the universe, he didn't start with the Big Bang narrative. He started with Hubble's observations of galaxy redshifts, explained what redshift meant in terms of light waves, showed how to calculate the relationship between redshift and velocity, then worked through what that implied about the universe's expansion. The Big Bang emerged as a conclusion from observations rather than as an assumption at the beginning. This pedagogical approach reflected Feynman's conviction that physics should be learned by doing, by working through calculations and seeing how observations constrain theories. Textbooks that presented finished theories without showing how they emerged from data gave students a false picture of how physics worked. They made it seem like theories sprang fully formed from brilliant minds, when in reality theories developed gradually through iterative interaction between experimental results and theoretical attempts to explain them. By focusing on this process rather than on polished final products, Feynman's lectures taught not just physics content but scientific methodology itself. The methodology became especially important when dealing with cutting-edge research where answers weren't yet known. Many physics educators teach established results confidently, as settled facts students need to learn. This works well for classical mechanics or electromagnetism, where centuries of testing have confirmed the theories. But in cosmology, where many questions remain open and many theories remain speculative, this approach can mislead students into thinking we understand more than we do. Feynman's alternative was to teach the questions alongside the answers, to show students what we knew definitely, what we thought was probably true, and what remained uncertain. This required more nuance and more time, but it produced students who understood not just current theories, but the epistemic status of those theories. The distinction between knowing and thinking becomes particularly important when considering the role of certainty in science. Popular culture often portrays scientists as people who deal in absolute certainty, who know the facts and can tell you definitively how things work. This stereotype does science a disservice because it misrepresents both what science claims and how it operates. Science doesn't produce absolute certainty. It produces varying degrees of confidence based on accumulated evidence. Some things we're very confident about because they've been tested extensively in many different ways and all tests confirm the same picture. The Earth orbits the Sun, atoms exist. DNA carries genetic information. These aren't absolute certainties in a philosophical sense, but the evidence for them is so overwhelming and varied that doubt would be unreasonable. Other claims have much less evidence supporting them. Dark energy exists and drives cosmic acceleration. This claim rests primarily on observations of distant supernovae showing that expansion is speeding up. The observations are solid, but they're relatively recent. They've been made by a limited number of research groups, and alternative explanations haven't been fully ruled out. We're fairly confident dark energy exists, but nothing like as confident as we are about atoms. Still, other claims have almost no direct evidence. The inflaton field drove cosmic inflation. Supersymmetric particles exist. String theory correctly describes quantum gravity. These are active research hypotheses, taken seriously by many physicists, but far from established facts. Feynman insisted on maintaining these distinctions clearly and never pretending that speculative ideas enjoyed the same evidential support as well-tested theories. This insistence on epistemic clarity extended to how Feynman talked about scientific consensus. In most scientific fields, consensus eventually emerges as evidence accumulates and theories are tested. When a theory consistently makes correct predictions and survives all attempts to falsify it, scientists gradually accept it as the best current explanation for the phenomena in question. This consensus is valuable because it represents the collective judgment of experts who have examined the evidence carefully. But consensus is not itself evidence. A theory isn't true because everyone believes it. It's believed because the evidence supports it. Feynman emphasized this distinction because he saw instances where scientific consensus hardened around ideas that hadn't been adequately tested, where social dynamics and theoretical elegance led to premature acceptance of hypotheses that remained unverified. The clearest example during Feynman's lifetime was the early reception of grand unified theories in particle physics. In the 1970s, theorists developed models that unified the electromagnetic, weak, and strong nuclear forces into a single framework at very high energies. These theories were mathematically beautiful and solved several outstanding puzzles. They made one clear prediction: protons should decay, albeit very slowly, with a half-life of perhaps 10 to the power of 31 years. Experiments were designed to detect this decay by watching large volumes of water for flashes of light produced when protons in the water molecules broke apart. The experiments ran for years. No decays were detected. The prediction failed. The simplest grand unified theories were ruled out. Feynman's response to this outcome, documented in lectures from the early 1980s, was telling. He didn't gloat over the failure. He didn't criticize theorists for proposing ideas that turned out to be wrong. Instead, he praised the episode as an example of how science should work. Theorists proposed a testable idea. Experimentalists built detectors to test it. The test gave a definite result that ruled out the simple version of the theory. Theorists went back to develop more complex versions that avoided the problem. This was the scientific method functioning properly, theories and experiments in dialogue, each constraining and guiding the other. The fact that the original theory failed didn't make it bad science. Proposing testable ideas that turn out to be wrong is how science progresses. What would have been bad science would be continuing to believe in the theory after it had been falsified, or proposing ideas that couldn't be tested at all. This distinction between good speculative science and untestable speculation guided how Feynman evaluated new proposals throughout his career. When a physicist proposed a new theory, Feynman's first question was always, what does it predict? What observations would confirm it? What observations would rule it out? If the theory made clear testable predictions, it was worth considering, even if those predictions seemed unlikely. If the theory was so flexible that it could accommodate any possible observation, then it wasn't really a scientific theory at all. It was a framework for organizing observations, potentially useful but not confirmable or falsifiable. Good theories took risks. They stuck their necks out and said that nature must behave in specific ways. This made them vulnerable to being proved wrong, but it also made them valuable because proving them right would tell us something definite about nature. This emphasis on risk and falsifiability came from Feynman's deep engagement with the philosophy of science, particularly the work of Karl Popper. Popper had argued that what distinguishes science from pseudoscience is not verification but falsifiability. Scientific theories must be capable of being proved wrong by observation. If no possible observation could contradict a theory, then the theory isn't scientific. Feynman found this criterion enormously useful as a practical guide for evaluating theories. It separated genuine scientific hypotheses from unfalsifiable claims that only looked like science. And it explained why theories that explained too much, that were compatible with any possible observation, actually explain nothing. A theory that predicts everything predicts nothing specific, and specificity is what makes predictions testable. Applying this criterion to cosmology separated legitimate scientific cosmology from cosmological speculation. The Big Bang model made specific predictions about the cosmic microwave background, about the abundances of light elements, about the relationship between redshift and distance. Each of these could have been wrong. Each could have falsified the model. The fact that observations matched predictions instead strengthened confidence in the model. But inflation, dark matter, and dark energy, while making some testable predictions, also contained enough free parameters that they could be adjusted to fit almost any observation. This flexibility made them harder to falsify and therefore, in Feynman's assessment, less compelling than theories with more rigid predictions. The question of what makes a theory compelling leads back to Feynman's views on the role of mathematics in physics. Mathematics is essential to modern physics. Without mathematical frameworks, we cannot make precise predictions or compare theories quantitatively. But mathematics alone is not physics. You can develop beautiful, consistent mathematical theories that have no connection to the physical world. Pure mathematics does this all the time, exploring abstract structures for their own sake. The difference between mathematics and physics is experiment. Physics requires that mathematical predictions match measurements. This seems obvious, but Feynman worried that modern theoretical physics sometimes lost sight of this requirement. Theorists would develop elaborate mathematical frameworks, find them beautiful and compelling, and start treating them as true before any experimental verification. This was backwards. Mathematical beauty might be a useful guide for suggesting theories to test, but it couldn't replace testing. The challenge, Feynman recognized, was that experimental testing had become increasingly difficult and expensive as physics pushed into new regimes. Testing theories of particle physics at very high energies required enormous accelerators costing billions of dollars. Testing cosmological theories required sophisticated telescopes and satellites, and years of observational time. The time between proposing a theory and being able to test it stretched from years to decades. This created a temptation to evaluate theories on purely theoretical grounds, to accept them because they were elegant, or because they solved puzzles, or because lots of smart physicists believed in them. But Feynman insisted this was dangerous. Without experimental discipline, physics risked becoming a purely mathematical enterprise, beautiful perhaps but disconnected from nature. This risk was not hypothetical. By the time Feynman died in 1988, string theory had been under development for nearly 2 decades without producing a single testable prediction about the physical world. The theory had generated important results in mathematics, had attracted brilliant researchers, had produced thousands of papers. But it still couldn't tell you what any particle's mass should be or what any force's strength should be. It had too many possible versions, too many ways to connect its abstract mathematical structure to observable physics. Each version gave different predictions, and without some way to choose between them, the theory couldn't make definite claims about nature. Some string theorists argued that this didn't matter, that the theory was so mathematically compelling that it must be true even without experimental verification. Feynman found this argument completely backwards. Nature didn't care about mathematical beauty. Nature did what it did, and physics had to accommodate itself to nature's choices, not the other way around. This commitment to experimental primacy shaped Feynman's entire worldview, not just his physics. He believed that reality had the final say in all disputes. You could argue about theories, debate interpretations, prefer one mathematical framework over another. But eventually, you had to check with nature. You had to make a measurement, perform an experiment, see what actually happened. And if your beautiful theory disagreed with that measurement, your theory was wrong, no matter how beautiful it was. This might seem like a simple principle, but Feynman saw many cases where people tried to evade it, where they adjusted their theories to fit contrary evidence, or questioned the measurements, or claimed the discrepancy didn't matter. Such moves were sometimes legitimate. Measurements could be wrong. Theories could be applied outside their domain of validity. But Feynman insisted on taking measurements seriously, on treating disagreement between theory and experiment as a crisis that demanded explanation, not something to be minimized or explained away. The most famous example of this attitude came not from cosmology but from Feynman's work on the Challenger disaster investigation in 1986. NASA had developed complex models of how the space shuttle's components behaved under various conditions. These models said that the O-rings sealing the rocket boosters would remain flexible and functional even at the low temperatures present during the Challenger launch. But Feynman did a simple experiment. He took a piece of O-ring material, put it in ice water to simulate launch temperatures, then compressed it. The material became stiff and didn't spring back. He did this during a televised commission hearing, demonstrating in real time that the O-rings failed at low temperatures, contradicting NASA's models. The demonstration was devastating because it showed that reality didn't care about sophisticated models. If the physical material failed when cold, then the models that said it wouldn't were wrong, period. No amount of theoretical argument could change the fact of the material's behavior. This same uncompromising empiricism guided Feynman's approach to cosmological questions. The universe was doing what it was doing, following whatever laws actually governed it. Our theories about those laws might be right or wrong or partially right. The only way to know was to check, to make observations and see if they matched theoretical predictions. When observations disagreed with theory, something was wrong with the theory, full stop. Maybe the theory was completely wrong. Maybe it was right in some regimes but not others. Maybe it was missing some effect or making an unjustified approximation. But the theory needed to change to accommodate the observations, not the other way around. This principle became particularly important with the discoveries of dark matter and dark energy. Both discoveries came from observations that didn't match theoretical expectations. Galaxies rotated faster than visible matter could account for. The universe's expansion was accelerating when theory predicted it should be decelerating. These were genuine surprises, moments when nature revealed something unexpected. The response could have been to question the observations, to look for systematic errors or alternative explanations that preserved existing theory. And indeed, researchers did check carefully for errors and did explore alternatives. But when the observations held up under scrutiny and when alternative explanations were ruled out, the physics community largely accepted that something new was needed, some component of the universe we hadn't previously known about. This was the right response in Feynman's framework. Unexpected observations were opportunities to learn something new, not problems to be explained away. But accepting that something new was needed didn't mean accepting any particular explanation uncritically. Dark matter and dark energy remained hypotheses, well motivated by observations but not directly detected. The search for dark matter particles continued in underground detectors around the world, trying to catch the rare collision between a dark matter particle and ordinary matter. These searches had not yet succeeded by 2025, though they had ruled out many possible types of dark matter particles. The nature of dark energy remained even more mysterious, with competing theories proposing everything from a cosmological constant to exotic fields to modifications of gravity on cosmic scales. Each proposal made different predictions about how dark energy should evolve over time or how it should affect the universe's structure. Testing these predictions required extremely precise cosmological observations, measurements of how fast the universe expanded at different times in its history. Such measurements were being made with increasing precision, but the uncertainties remained large enough that multiple theories remained viable. If you appreciate this kind of clear, evidence-driven explanation, subscribing and liking the video helps more of this content reach the right audience. You'll also find many other videos on the channel that follow the same approach. Feynman's approach to cosmology, developed over 4 decades of teaching and research, offered a distinctive vision of how to study the universe scientifically. Not through grand narratives or elegant theories accepted on faith, but through patient accumulation of observations, careful development of testable theories, and honest acknowledgement of what remained unknown. This vision didn't promise final answers or ultimate understanding. It promised something more valuable, a reliable method for distinguishing what we actually knew from what we merely hoped or suspected or preferred to believe. In an age when cosmology offers increasingly elaborate stories about the universe's birth, evolution, and fate, Feynman's insistence on epistemic discipline, on marking clearly where observation ended and speculation began, remains as relevant as ever. The cosmos still holds its mysteries. We are still, in the largest sense, near the beginning of understanding it. But the path forward lies not in premature certainty but in careful questioning, in precise measurement, in calculations checked against nature at every step. This was Feynman's legacy, not a new cosmology, but a more honest way of doing cosmology itself.